It's very far above my expectation.
Show the customers what we can do with our product.
Thank you for your participation in today's webinar, Pulse Flour Opportunities in Bakery Products. My name is Tanya Durr. I am the Manager of Food Innovation and Marketing at Pulse Canada, and I'll be the moderator of today's webinar. Before I introduce our speaker, I'd like to run through some housekeeping items. On the bottom left of your screen, you'll see some screen sizing options. You have the ability to switch to full screen to better view the presentation. Today's webinar is being recorded, and it will be posted on the Cigi website shortly following this live presentation. The Cigi website address is www.cigi.ca. Please feel free to ask questions at any time during the presentation using the question and answer box on the right side of your screen. You can also use this Q&A box to let us know if you are having any technical issues. Please send questions to WebEx presenter. Now I'll introduce today's presenter, Lindsay Bourré. Lindsay Bourré joined Cigi's Analytical Services Laboratory in 2007. In 2010, she began working in pulses and is currently a technical specialist focused on the Cigi Pulse Milling and Utilization Project. Activities of this project include investigating the effect of milling method on pulse flour functionality and the inclusion of pulse flours as ingredients in various food applications. Lindsay holds a Master of Science degree in Food Science from the University of Manitoba. Her thesis examines the incorporation of pulse flours as ingredients in Asian white salted noodles. I will now turn it over to Lindsay to begin today's presentation.
Thanks, Tanya. Good morning, everyone. First of all, thank you for joining us, and welcome to this morning's webinar on pulse flour opportunities in bakery products. The purpose of this webinar is to look at some of the work that we have been doing here at Cigi and highlight the work that we have done looking at pulse flours as functional ingredients in cookies, pan bread, pitas, and tortillas. For the next half an hour or so, I'm going to first quickly talk about Cigi and the Pulse Milling and Flour Utilization Project. Next, I will discuss some different pulse flours and look specifically at some of their functional, compositional, and physical properties that will give some indication of how these flours will perform in baked products. I am going to discuss 4 product applications: cookies, pan bread, pita bread, and tortillas, and look at how pulse flours with different properties affect end product quality. Then I'll finish with a few slides to discuss the potential of using pulse flours in gluten-free product applications. Cigi is the Canadian International Grains Institute and is based in Winnipeg, Manitoba. It is an independent market development institute that was established in 1972. Our mission is to create profitable opportunities for Canada's field crops through the delivery of technical expertise, support, applied research, and customized training. Our technology facilities include capabilities in Asian products such as noodles and steamed breads, extruded products such as pasta and snack foods, flour milling both on a lab and pilot scale, pilot and test baking facilities, and a pulse processing and specialty milling facility, as well as an analytical laboratory. In 2010, Cigi and Pulse Canada partnered on the Pulse Milling and Flour Utilization Project. Although research using pulse flours is not necessarily new, there was a lack of research surrounding pulse flour processing and utilization. Therefore, there was a need for a systematic study on the effect of milling technologies on the compositional, functional, and end-use characteristics of pulse flours. With this in mind, this 4-year project began. The objectives of the Pulse Milling Project are to expand our knowledge about pulse flours, to increase our understanding of how milling technologies affect pulse flour quality, to optimize performance of pulse flours in a range of food product applications, and to work with commercial flour millers and food processors to expand the usage of pulse flours. This project is being funded by the Canadian Special Crops Association, Saskatchewan Pulse Growers, Alberta Pulse Growers, and Agriculture and Agri-Food Canada. Before I get into using pulse flours as ingredients, I just want to quickly discuss some of the more marketable attributes of pulses. Pulses are nutritional powerhouses that are high in dietary fiber, high in protein, and low in fat. They are also high in vitamins and minerals. Pulses are sustainable. In farmers' fields, pulse crops are able to fix their own nitrogen and therefore require less fertilizer and are used in crop rotations to keep fields healthy. They are widely available. This year, yellow pea and red lentil production in Canada is at an all-time high. And lastly, pulses are gluten-free and are a non-GMO crop which appeals to many consumers. Although pulses on their own tell a good story, we need to look at pulse flours as ingredients and what makes them work as functional ingredients. We will take a look at physical characteristics such as particle size and color, compositional differences in dietary fiber and protein, and finally functional characteristics like water absorption capacity, starch damage, and pasting properties. All of these attributes affect how a pulse flour will work in a food system and therefore affect end product quality. As mentioned previously, an objective of the pulse milling project was to examine the effect of milling method on pulse flour quality. To do this, 4 different milling technologies were chosen. The hammer mill, pin mill, roller mill, and stone mill were all used on a commercial scale to produce pulse flours. 2 different settings were used on the pin mill to produce a fine and coarse flour. Yellow peas and red lentils were milled using each of these 4 milling methods. Furthermore, whole yellow peas and split yellow peas were milled, and whole red lentils and split red lentils were milled, thus creating a total of 20 different pulse flours to work with. The next 4 slides are showing some of the selected data that was generated from the flours that were produced. Here you are looking at the split yellow pea flours. So first, you can see that the milling methods produce flours that had different particle size. The pin mill and roller mill produce flours with finer particles, whereas the hammer and stone mill produce flours with larger particles. We also see differences in starch damage, with the more aggressive milling methods like roller, stone, and the pin mill set to a higher setting have higher starch damage compared to the hammer and less intense pin milling flours. Here are the whole yellow pea flours. Again, we see similar trends in particle size, with the stone mill producing flours with the largest particles and the pin mill fine producing the smallest particles. But among the whole flours, the average particle size is much larger than the split yellow pea flours. This is due to the hull, which is difficult to mill down to a fine particle size. This also explains the higher fiber content that we see in the whole flours. These average particle size values also show that the pin mill, set to a fine setting, is the only milling method that we use that was able to significantly reduce the size of the hulls. The presence of the hull also increases the water absorption capacity of the flour and decreases the viscosity and starch damage. Now moving on to the red lentil flours. As was seen in the milling of yellow peas, stone milling produces flour with the greatest average particle size, while pin milling on a fine setting again has the smallest average particle size. Higher starch damage values are seen in the pin mill fine and roller mill flours, which is similar to what was seen with the split yellow pea flours. Also, the split red lentil has higher starch damage and fairly similar water absorption capacities compared to the split yellow pea flours. In the whole red lentil flours, as was seen with the yellow pea flours, the presence of the hull produced flours with a larger average particle size, with the exception of the pin mill fine flour. Not surprisingly, higher water absorption capacities were observed for the whole flours as well. The red lentil flours had a higher protein content compared to yellow pea flours and slightly lower dietary fiber values. Now that you've seen some of the flour properties of both yellow pea and red lentil flours, we will get into the product applications, the first being cookies. This is the formulation that was used and is from the American Association of Cereal Chemistry. It is approved method 10-53, which examines the baking quality of cookie flour. We baked a reference sample using a commercial pastry wheat flour and then used this wheat flour in our composite flour blends with 30% pulse flour from each milling method that I just described. This graph is showing the width of the yellow pea flour cookies. The hammer and stone mill flours produce cookies with the greatest width and that were most similar to the reference sample. We can also see here that cookies made with split flours had greater widths compared to those made with whole flours. The cookies with the greatest height were produced from the pin milled and the roller milled flours, which is consistent with these flours producing cookies that were less wide than the other milling methods. The cookies made with the whole flours, pictured on top, produced thicker cookies than those produced with the split flours, which are pictured on the bottom. The texture of the cookies was measured using a 3-point bend test. Among all milling methods, the pin milled fine and the roller milled flours produced cookies that required the most force to break. For all methods, cookies required more force to break compared to the split flours milled using the same method. In addition to the yellow pea flours, cookies were also made using all the red lentil flours that were previously discussed. All of the cookies made with red lentil flour had widths greater than the reference. This was different than what was seen with the yellow pea flour cookies, where the stone and hammer mill flours were closer to the reference, while the other milling methods were below. Despite these differences with the reference, the cookies made with red lentil flours generally followed the same trends as the yellow pea flour cookies for cookie width, with flours with larger particles producing cookies that were wider compared to those made with split flours. Here you can see the differences in height among the cookies made with the red lentil flours. The cookies made with whole flours are on the top and split flours are on the bottom. Again, cookies with the greatest width, which in this case are the stone and hammer mill flours, produce cookies with lower height or thickness than the pin milled and roller milled flours. Here is an image of cookies that were made using the split and whole red lentil flours. It allows you to see the difference between not only the split and whole flours, but also between milling methods. The top row is the whole red lentil flour, where you can actually see the hull. The pin-milled fine flour is the milling method that is most effective at reducing the hull size, which is why you don't see the specks that you see in the cookies milled using the other milling methods. The cookies in the bottom row are made from the split flours, and you can see that there are no specks and they have a desirable golden color. Once again, the 3-point bend test was used to evaluate the texture of the red lentil cookies. There were noticeable differences between the whole and split red lentil flours, with the whole flours requiring considerably less force to break compared to the split flours. Although the same trend was observed in that the flours with a finer particle size required more force to break among both red lentil and yellow pea flour cookies, differences between the split and the whole flours occurred. Split red lentil flours produced cookies that were harder than those produced with whole flours, while split yellow pea flours produced cookies that were softer than those with whole flours. Pulse flours can be successfully added to cookie formulations. The type of cookie that is desired, for example, a chewy versus a crisp cookie, will determine what type of pulse flour will work best. Flour properties such as particle size and dietary fiber content had the biggest impact on cookie quality. Flours with larger particle size produced cookies that were wider and thinner and less firm compared to flours with smaller particles. Having said that, differences were observed between whole yellow pea flour and whole red lentil flour, enforcing the need to recognize that different pulse types offer different functional properties. Next, we will move on to a totally different baked product, and we'll look at the addition of pea flour to pan bread. So here's a formulation that was used for pan bread containing 15% whole yellow pea flour. A whole wheat pan bread was made to minimize the color differences that would typically be observed if we were to make a white pan bread. Molasses was used in the formulation to complement some of the flavors associated with yellow peas. The amount of water added was kept constant for all milling methods in order to see the effect of milling method on end product quality. On the right is an example of a nutrition label for a pan bread using the formula that I just showed you. In Canada, a fiber claim stating a good source of fiber could be made on this bread product. There are also 8 grams of protein per serving. The pan bread was processed here at Cigi in the pilot scale bakery and was baked and evaluated by Tony Tweed, who is a master baker with over 40 years baking experience. While preparing the bread, the dough properties were evaluated after mixing and again at the molding stage. The whole pin-milled fine flour had the best dough properties after both mixing and molding and exhibited the least stickiness among the 4 flours. The hammer and roller mill flours had the stickiest dough properties at both stages of evaluation. I've included this photo, which is a cross-section of each bread that was baked, so you can see the differences among the milling methods. The bread was evaluated for crumb color, texture, softness, resilience, and crumb strength, and given a total score out of 50. The pin-milled fine flour produced a loaf of bread with the best quality score, while the roller mill flour produced bread with the lowest score. Loaf height was also measured. The pin-milled fine flour produced pan bread with the greatest height at 124 centimeters, followed by the roller milled, and then lastly the stone and hammer milled. Here you can see a comparison between the breads made with the whole pin-milled fine yellow pea flour and the whole roller-milled flour. You can see the differences in internal characteristics, with the pin-milled fine flour producing bread that has a uniform crumb structure and uniform cell distribution. The bread made with roller-milled flour has larger cells and less uniformity. Flatbreads, like pitas, are a good product to add pulse flours to, as they don't depend on gluten for their structure as much as a product like pan bread does. Therefore, replacing some of the wheat flour and pita breads with pulse flours is less structurally problematic compared to pan breads. So here is the formulation that was used to make 30% yellow pea flour containing pitas. A Canada Western red winter wheat was used as a reference, and in the composite flours that had a protein content of approximately 11%. The amount of water that was added to the formulation was reduced for the yellow pea flour containing pitas to reduce stickiness. The amount of water in the yellow pea flour pitas was kept constant for all milling methods. Like the pan bread, the pitas were produced in our pilot bakery here at Cigi with certain adjustments to processing. In addition to reducing the amount of water that was added in a formulation, adjustments were made at different stages. Mixing time was decreased from 6 minutes to 5 minutes. Intermediate proofing time decreased to 10 minutes compared to 20 minutes for the reference sample, and baking time decreased by 10 seconds to 65 seconds. All of the pitas made with yellow pea flour produced a pocket. In addition to forming a pocket, there were no significant differences observed among milling methods for the pocket height of pitas. Within milling methods, split flours generally produced a pocket slightly higher than the whole flours. The split stone mill flour produced a pita with pocket height most similar to the reference. This gives a better indication of just how well these yellow pea flours performed in the pita bread application. Here you can see that every milling method did produce a pocket. To measure texture, a puncture test was performed. As was seen with the pocket height, no significant differences were observed among milling methods. All pitas made with yellow pea flour required slightly less force to puncture in comparison to the reference sample. When comparing the split to the whole flours, within milling methods, the whole flours produced pitas that required slightly less force to puncture. The same test was performed on the bottom layer of the pitas, and like the top layer, no significant differences were observed. Here you can see the tops of the pitas made from each milling method, as well as the reference. The pitas made with the whole flours are presented in the top row, and in the bottom are the pitas made with the split flours. You can see that they all have a desirable golden color. You will notice that they are a bit darker than the reference. Pulse flours are higher in the amino acid lysine, which results in an increased browning during baking. This is the reason the baking time was reduced by 10 seconds. So the last product that I'm going to discuss are tortillas. Here is the formulation used. Again, we made a reference pita using 100% Canada Western red winter wheat, which had a protein content around 11%. We used this flour in our composite flour blends with 30% yellow pea flour. The diameter of the tortillas were measured and presented here. All of the yellow pea flours produced tortillas that had diameters comparable to the reference. The split flours tended to produce tortillas slightly larger than the whole flours milled using the same milling method. Texture was measured using the same puncture test that was performed on the pitas. All of the tortillas made with yellow pea flour required less force to puncture than the reference. For all milling methods, the whole flour produced tortillas with texture that was more similar to the reference. The only milling method in which this was significantly different was the pin-milled coarse flour. Here you can see the rollability of the tortillas on day 1 and again on day 3. The whole, larger particle flours produced tortillas similar to the reference and had the best rollability scores. The flours with the finer particles produced tortillas with the lowest scores. Finally, like I showed you with the pitas, here you can see the tortillas all together to compare, and you can see that they have similar diameters and have acceptable color with desirable browning characteristics. So overall, yellow pea flour can be successfully added into different flatbread applications. In tortillas, we saw that whole yellow pea flours with larger particle sizes produce tortillas with textural characteristics similar to the reference. In pitas, we saw that yellow pea flour pitas were able to form a pocket regardless of flour properties and without affecting texture of the end product. So for the last few minutes of this webinar, I would like to spend talking about some of the work that we've begun at Cigi looking at pulse flours and gluten-free baking. I know that I already mentioned the health benefits of pulses, but I just wanted to mention them again, as one of the biggest criticisms of baked gluten-free foods is that they are often high in calories, high in fat and sugar, and void of many nutrients. So I just want to say again that pulses are high in protein, high in dietary fiber, and contain many vitamins and minerals. As well, they are low in fat and sodium, making them a good option in gluten-free applications. Some of the preliminary work we've been doing is looking at some gluten-free flatbreads like pitas and tortillas. This is an example of a formulation for tortillas where we substituted some of the rice flour with a whole yellow pea flour and tapioca starch with pea starch. Here are two nutrition labels that illustrate the impact of adding the pulse flour and starch. On the left, we have a commercially available gluten-free tortilla product compared to the one made with yellow pea flour and starch. You can see that both the dietary fiber and protein values increase from 1 to 3 grams. This now means that this product would be eligible for the fiber claim, Source of Fiber, here in Canada. We have also begun work looking at gluten-free pitas, again using yellow pea flour, this time with tapioca, starch, and white and brown rice flour. The nutrition label for the gluten-free pita shows that it contains 4 grams of protein and 3 grams of fiber, which again, making it eligible for a nutrient claim that states it's a source of fiber. Lastly, here is a formulation for gluten-free pizza crust that was developed using yellow pea flour and tapioca starch. Adding the yellow pea flour to the gluten-free pizza crust resulted in a protein content of 6 grams and 4 grams of fiber per serving, again in Canada allowing for a nutrient claim of a high source of fiber. Here at Cigi, we are going to continue working on gluten-free products using pulse flours and work on establishing a link between the functional attributes of pulse flours and how they affect end product quality in different gluten-free foods. We have shown that the different functional properties of different pulse flours does affect end product quality. Therefore, understanding these flour characteristics will aid in the successful inclusion of pulse flours in certain gluten-free applications. I would like to invite all of you to check out our website and follow the progress of the project on www.cigi.ca. Here you can access all of the work done to date on the pulse milling project and follow our progress. Posted on the website are all of the flour data sheets that I presented today, as well as product profile sheets, research posters, past webinars, and videos. This webinar will also be posted to the website so you can share with colleagues or anyone you think may be interested. I have also included my email here as well as Heather Maskis's, who is the Pulse Milling Project Manager. If you have any questions, comments, or inquiries, please do not hesitate to contact us. We would love to hear from you. Thank you.
Thank you for a great presentation, Lindsay. We do have time for a few questions, and you can, again, if you have any questions, you can enter your questions in the question and answer box on the right-hand side of your screen, just at the bottom, and please send questions to WebEx Presenter. Now, as we wait for some questions to come in, I wanted to also mention that we would like to acknowledge the support of Agriculture and Agri-Food Canada, the Saskatchewan Pulse Growers Association, Alberta Pulse Growers Association, and the Canadian Special Crops Association, who are the funders of the Pulse Flour Milling Project, and we'd like to thank them for also making this webinar possible. Okay, so we have a few questions now that are coming in, and this one is regards to the cookie work that you did. Your slides showed that there were some specks in the whole red lentil flour cookies, and the question is, do you get these specks in the whole yellow pea flour as well?
When we add the whole yellow pea flour to cookies, the color of the hulls is more neutral, and therefore we don't see the speckiness that in the red lentil application.
Okay. Another question here. There was a lot of information on the red lentils and the yellow peas, and were there any other work done on pulse flours like coming from chickpeas or navy beans? We have done some work with chickpeas and navy bean flours, but we're focusing most of this work looking at yellow peas, red lentils, and going to be doing some work with green lentils just because they are, we have the highest capacity for production in Canada with those pulse crusts. So we want to ensure that they're available for anyone who's interested in using them. Okay. Here's another one coming in. There was some mention about water addition being variable in your formulations with pulse ingredients. Can you please elaborate on this?
Usually we see when we add pulse flours to bakery products that we have to reduce the amount of water that we add. This is because we get a lot of dough stickiness, so even though they're higher fiber and we see increased water absorption capacities, they actually aren't able to hold onto the water like what is done in wheat systems. So we actually reduce the amount of water that we generally add.
We've got a few more questions here. Lindsay, how does removing the wheat and replacing it with pulse flour change the handling of the doughs during processing?
For some applications, we see that it does increase the stickiness, and that's why we do have to make those processing changes that I was talking about.
Okay. Can you please comment on the flavor profile changes with the addition of pulses?
Sure. There's definitely, when we add some of these pulse flours, there definitely is some increased flavors associated with pulses, which is why you see that we add levels of up to 30% because we don't want to compromise flavor too much. So the purpose of a lot of our research is just to look at the functional properties. So we're not adding flavoring, we're not adding other ingredients that either complement or help with the flavor except for with the bread work that we did. So although there are strong flavors associated with pulse flours, there are ways that you can minimize this in products. And this again is with the use of other ingredients as well as there's some work being done with pre-treatments that looks at how this eliminates flavors that some people may not find desirable with pulse flours.
Could you talked about starch damage. Could you comment on the method used for measuring this?
Yep, the starch damage was measured using an enzymatic method. So we used a Megazyme starch damage kit to do the measurements. If there's any, like with regards to methods, we have all of the methods and how we do them on the website as well. So if anyone wants more details, they can look right on there, or I can get back to anyone with the details. I can look them up for them.
Well, if anyone has any additional questions after the webinar, you can email Lindsay Bourré or Heather Maskus at the email addresses on the computer screen. And then Lindsay has some more comments to make.
Sorry, I see a question too that there's if we've done work with any other products, and we do have a lot of information on some work we've done with pasta, Asian noodles, extruded snacks and puffs, and this is all available again on our website as well. You can contact Heather and I. We're more than happy to share it with you and discuss some of the results.
Great. So we will conclude our webinar presentation on pulse flour opportunities in bakery products. And again, the recording was made today on today's webinar and will be made available on cigi.ca. And if you would like to learn more about the Canadian pulse industry, you can also go to pitas.com for more information. So thank you, everyone, for your participation and interest today, and we hope that you enjoyed the webinar presentation and that you can join us again next time. Thank you.